Whenever movement takes place between surfaces that are in contact with each other, friction, or resistance to the movement, occurs. Friction between the moving parts of industrial equipment can cause excessive heat and wear. So lubrication is used to help reduce and control friction. Lubrication is the act of applying a substance called a lubricant that creates a slippery barrier between surfaces that would otherwise come in contact. In this part, we'll look at some of the types of friction that can occur. We'll also look at different kinds of lubricants and describe various levels of lubrication. Moving parts generally experience one or more of three basic types of friction: sliding, rolling, and fluid. Sliding friction occurs when one surface slides across another. This type of friction offers the most resistance to motion, so machines are usually built to minimize or eliminate it. One way of building a machine to minimize sliding friction is to place rolling elements between the moving surfaces. This is the principle behind rolling contact or anti-friction bearings. Although rolling contact bearings are used to reduce sliding friction, they do experience another type of friction, rolling friction. Rolling friction is the resistance to motion that occurs when one object rolls over the surface of another. Rolling friction is considerably less severe than sliding friction, but rolling contact bearings must still be properly lubricated to reduce heat and wear. Another way to reduce sliding friction is to separate two sliding surfaces with a film of lubricant. As long as the surfaces don't touch, sliding friction is eliminated. Some fluid friction exists within the lubricant, but it's much less than the sliding friction. Fluid friction is the resistance to motion that exists in a fluid. For instance, fluid friction is what makes it difficult to walk rapidly in deep water. Three common kinds of lubricants are liquids, greases, and solids. Liquid lubricants are oils, mineral oils, which come from refined crude oil, and synthetic oils, which are man-made compounds, are commonly used in industrial applications. Greases aren't strictly liquid or solid. Instead, they typically soften when the temperature rises and stiffen when the temperature falls. Solid lubricants are made from substances that retain their shape under normal conditions. Solid lubricants include some forms of metal, such as molybdenum disulfide, and several solid chemicals, such as graphite. When they act as a lubricant, the solid materials create layers that slide over one another. This reduces the friction that would occur if metal parts were in direct contact. Solid lubricants, such as the material whose trade name is Teflon, are also used as chemical coatings that prevent metal-to-metal contact by providing a solid covering for a metal surface. Chemical coatings are generally used in combination with another kind of lubricant. For example, if an oil film breaks down and allows two surfaces to come in contact, the chemical coatings provide backup lubrication. Different levels of lubrication are possible. One level is no lubrication. When there's absolutely no lubricant between moving surfaces, the surfaces are dry. This condition causes the maximum friction between moving surfaces and should be avoided as much as possible, except for applications such as braking, in which maximum friction is desired. A second level of lubrication is mixed film lubrication. To better understand what happens when this occurs, we'll use this illustration that shows a highly magnified portion of two mating surfaces. Under magnification, you can see that the mating surfaces actually have many irregularities, or peaks and valleys. Mixed film lubrication occurs when the mating surfaces are only partially lubricated, and metal-to-metal contact occurs between the high points of the surfaces that are moving across each other. Part of the load is relieved by the lubricant, but the high points of the mating surfaces take most of the load, which results in friction and wear of the surfaces. Mixed film lubrication is by no means an ideal situation, but it is a common occurrence. A third level of lubrication is film lubrication, also called full film lubrication. It occurs when moving and stationary surfaces are separated by a film of oil. Film lubrication is the preferred level of lubrication for bearings. To see the basics of how film lubrication works, we'll use this illustration of a plain journal bearing. The bearing has a sleeve that surrounds a shaft. The space between the bearing and the shaft contains lubricating oil. While the shaft's at rest, the weight of the shaft squeezes most of the oil out from between the shaft and the bearing. This places the bearing and the shaft in metal-to-metal contact. But when the equipment is started, the shaft begins to roll slowly, and the motion drags oil underneath the shaft. Oil sticks to the shaft as the shaft turns, and the oil is carried between the two surfaces. The shaft is lifted away from the surface of the bearing by a film of oil. As the rotational speed increases, more and more oil is drawn under the shaft, and eventually, full film lubrication is achieved. The layer of oil supports the shaft and prevents it from touching the bearing surface. In this part, we'll examine some of the most significant properties of lubricants. One of the most critical properties of liquid lubricants is viscosity. The thicker lubricant has a greater resistance to flow, so it has a higher viscosity, while the thinner lubricant has less resistance to flow and therefore a relatively low viscosity. The thinner the lubricant, the lower the viscosity. Viscosity is affected by temperature. Higher temperatures cause lower viscosity because lubricants thin as temperature increases. On the other hand, lubricants thicken as temperature decreases. Both cases are significant because a lubricant won't lubricate properly if it's either too thick or too thin. If a lubricant is used where large changes in temperature occur, the lubricant's viscosity index is important. The viscosity index is a measure of the lubricant's viscosity change in relation to temperature change. If, when temperature changes a large amount, the lubricant's viscosity changes a small amount, the lubricant has a high viscosity index, or VI. If, when temperature changes a relatively small amount, the lubricant's viscosity changes a large amount, the lubricant has a low VI. Consequently, the temperature at which the viscosity measurement was obtained must be stated. This information is important because the same lubricant will have different viscosities at different temperatures. In addition to viscosity, several other properties that affect lubricant performance are used by manufacturers as they develop lubricants for various applications. One of these properties is pour point. It's the lowest temperature at which a lubricant will pour or flow. Below the pour point, the lubricant will be too viscous or thick to flow by gravity. A low pour point indicates that the lubricant flows at low temperatures. A high pour point indicates that the lubricant needs higher temperatures to flow. The pour point is especially critical in machinery that must run in cold weather and in equipment that's used in refrigeration systems. Two other temperature-related properties of lubricants are flash point and fire point. The flash point of a lubricant is the lowest temperature at which the lubricant's vapor will ignite when it's exposed to a source of ignition. The fire point is the lowest temperature at which the lubricant will burn steadily when it's exposed to a source of ignition. This occurs because enough vapor is created to cause continuous burning. If either the flash point or the fire point is exceeded, a fire hazard exists. Resistance to oxidation is another significant property of lubricants. It refers to a lubricant's resistance to reacting chemically with oxygen when exposed to heat and air. You see, many industrial lubricants are made from hydrocarbons. When the hydrocarbons are exposed to heat and air, the chemical reaction called oxidation occurs. Oxidation causes chemical changes that destroy a lubricant's effectiveness and lead to the creation of deposits such as sludge and varnish. Oxidation also produces acids that cause rust and corrosion. The oxidation process is normally slow, and over time, most lubricants do tend to oxidize. Oxidation can speed up, however, if the lubricant splashes around excessively or if it's exposed to high temperatures. A lubricant's resistance to forming an emulsion is also important. Basically, an emulsion is a mixture or suspension of components that are difficult to separate once they've been combined. The process that causes the formation of an emulsion is called emulsification. A lubricant that resists forming an emulsion is usually desirable because an emulsion of lubricant and water has poor lubricating qualities. Equipment manufacturers generally specify appropriate lubricants for their equipment, depending on how the equipment will be used. In turn, workers are responsible for making sure that they use the type of lubricant that's been specified. Various factors determine the appropriate lubricant for a given situation. For instance, pressure or load affects the selection of a lubricant. An application with relatively high pressure requires a lubricant that won't flow away from where it's needed when the pressure increases, such as when gear teeth mesh. Applications that involve relatively high loads or pressures typically require greases, solid lubricants, or high viscosity oils. Speed is also a factor in lubricant selection because there's a higher rate of wear at high speeds than at low speeds. Generally, low viscosity oils provide lower friction and better heat transfer at high operating speeds than high viscosity oils do. In short, low viscosity lubricants are more suitable for components such as certain bearings where the loads are light, the speeds are high, and the system is fully enclosed. High viscosity lubricants are more suitable for components such as open gears where the speeds are low, the loads are high, and the system is not enclosed. Temperature also affects a lubricant's viscosity. If wide, rapid variations in temperature are involved, a lubricant with a high viscosity index is usually needed. Temperatures must not exceed the lubricant's flash point and fire point. On the other hand, temperatures must not be lower than the lubricant's pour point. Substances or conditions in the environment where a lubricant will be used also affect lubricant performance. For example, a lubricant must be able to withstand chemicals that may tend to break down the lubricant. And if there's water in a system, a lubricant that resists emulsification is usually required. In most cases, lubricants contain additives which also affect lubricant selection. An additive is a substance that's added to a lubricant to provide or improve a specific property. Such substances are usually added by the lubricant manufacturer. To make sure that they use the correct lubricant for a specific piece of equipment, workers usually refer to the lubrication chart that's supplied by the equipment manufacturer. The lubrication chart applies only to that particular piece of equipment, and it should not be used as a lubrication guide for any other equipment. Often, each lube point or equipment part that requires lubrication, as indicated on the lubrication chart, is shown and numbered on an illustration that accompanies the chart. In turn, the numbers from the illustration are listed on the lubrication chart, in this case, in the index numbers column. For instance, item number 2 from this illustration is identified as the boom pivot shaft on this simplified lubrication chart. Reading across that line on the chart, you can find the number and type of lube points. In this case, 2 grease fittings, and the recommended type of lubricant and method of application. In this case, multi-purpose grease, abbreviated as MPG, applied with a pressurized grease gun or pressure gun. You can also find out how frequently the boom pivot shaft should be lubricated, which is every 10 hours. Proper storage of lubricants is essential to prevent contamination and unnecessary waste of the lubricants, as well as fires, spills, and accidents. For these reasons, the federal government and many state governments have strict regulations that apply to the storage and handling of lubricants. In this part, we'll cover some basic procedures for ensuring that lubricants are stored safely. After lubricants have been delivered, they're often stored in their containers for a long time before they're used. Depending on a facility's available space, the containers may be stored indoors or outdoors. Two major problems with outside storage are dirt and weather. So store lubricants in a location where there's a minimum of dust and dirt. Also, use a temporary covering like a tarp or a permanent covering like this three-sided shed to protect the containers from the weather. Generally, metal drums of lubricant should be stored either upright on pallets or horizontally on racks that keep the containers off of the ground. You see, storing a metal drum on a rack keeps the metal of the drum from contacting the ground or standing water. This helps prevent the destructive chemical reaction of corrosion from occurring. In addition, storing a drum on its side prevents water from collecting on the top of the drum. Water that's allowed to collect here can eventually penetrate the seal around the drum's opening and contaminate the lubricant that's inside the container. Most lubricants are combustible, which makes fire a hazard that's associated with storing these materials. One reason for storing lubricants outdoors is to minimize the damage from a fire by keeping the lubricants away from buildings, equipment, and work, such as welding or cutting, that involve sparks or open flames. Also, always keep an appropriate type of fire extinguisher in the storage area. When lubricants are stored indoors, weather is less of a problem than with outdoor storage. But contamination, spills, and fire are still hazards that must be dealt with. Store lubricants in a fireproof room or building that's clean, well lighted, and well ventilated. The storage area should have a fire extinguishing system that can be controlled manually as well as automatically. Also, keep an appropriate type of portable fire extinguisher in the storage room. Position storage racks or shelves so that all lubricants can be reached easily. Make sure that all containers are plainly marked to identify their contents, and store the containers so that their markings can be clearly seen. If possible, store opened lubricant containers and containers of contaminated lubricants separately from new unopened containers. To dispense lubricant from a drum by gravity flow, store the drum in the horizontal position on a rack and equip the drum with a spigot that has a drip-proof valve for withdrawing the lubricant. If you must store a drum in the vertical position, you'll probably have to pump the lubricant out of the drum. Store cans or pails of lubricant neatly on shelves or on the floor. Finally, repair leaks promptly and clean up any drips or spills immediately. In this part, we'll look at common types of lubrication equipment for industrial applications. We'll begin with a grease gun. Hand-operated grease guns, or lever guns, are often used to grease bearings. Typically, the nozzle end of the gun is attached to a grease fitting on the bearing housing, and the gun's hand lever is pumped to apply grease through the fitting to the equipment's bearings. Grease guns enable you to develop high pumping pressure with little effort. In fact, grease guns can develop pressures in excess of 10,000 psi, which can damage seals. So you must operate grease guns with care. A very common way of filling some hand-operated grease guns is simply to slip a cartridge of grease into the barrel of the gun. Other types of grease guns can be filled quickly and easily with a filler pump that's clamped onto a bulk grease container, then attached to the gun. Power-operated lubrication equipment can be portable, like this pneumatic or air-powered grease gun. Or it can be permanent, like this centralized lubrication system that's designed to lubricate the bearings on several machines automatically. This illustration shows a typical centralized lubrication system. A motor-driven pump forces lubricant from a reservoir through lines in the system. A metering device on the lines measures out the correct amount of lubricant to inject for each bearing. Internal lubricators are typically used for the bearings of an internal combustion engine, an air compressor, or a gearbox. In this gearbox, oil is pumped from a reservoir through oil lines inside the machine. Then a gear that's mounted on a separate shaft rotates through the lubricant that's inside the gearbox and carries the lubricant onto the other gears. In this part, we'll talk about some standard procedures and precautions that are associated with handling and dispensing lubricants. Generally, when a lubricant is needed in a facility, workers move the lubricant containers from bulk storage to a central location in the facility where the lubricant can be dispensed. If a lubricant is taken from outside storage in cold weather, it should be allowed to warm up indoors before it's used. Low temperatures can thicken lubricants and make them unusable until they've been thoroughly warmed. As a rule, a lubricant container should be cleaned before it's opened to prevent dirt or debris from the container getting into the lubricant. When a container is opened and lubricant is removed, the container should be resealed as soon as possible to protect the remaining lubricant from contamination. Different lubricants may have incompatible additives, so when a lubricant is added to a partially full system, the type of lubricant that's added must usually be the same as the type of lubricant that's already present. When more than one lubricant is dispensed from the same location in a facility, it's important to identify each lubricant properly. Of course, the original shipping container must clearly state what lubricant the container holds. But any time a lubricant is placed in another container, the new container must also be clearly and correctly labeled. Lubricant should never be returned to its original container after it's been removed. That could contaminate the entire contents of the container. Likewise, contaminated or waste lubricant storage must be clearly marked. Different methods can be used to remove or dispense lubricants from their containers so that the lubricants can be put to use. We'll look at two of the most common methods for dispensing oil. One way to dispense oil from a drum or a barrel is to use a barrel pump that fits into the container. The first step in installing a barrel pump is to clean off the top of the drum. Then open the drum, and if there's a drum seal, remove it. Next, clean the pump and insert it into the drum. And finally, tighten the pump securely to the drum. For the barrel pump to work properly, the drum must be vented. This is usually done by removing a small vent cap from the top of the drum before you start to pump. When you're done pumping, replace the vent cap to prevent contamination of the lubricant. Another way to dispense oil from a drum is with a spigot that has a leak-proof valve. The drum must be positioned on its side. Sometimes a drum with a spigot is placed in a rocking frame. To dispense oil from the drum, the frame is rocked forward so the drum lies on its side. The drum may then be left in this position until it's empty, or if necessary, it can be rocked back into the upright position. With the drum vented, open the spigot and withdraw the oil from the drum. When the desired amount of oil has been withdrawn, close the spigot and the vent cap. When lubricating oil becomes contaminated or can no longer provide adequate lubrication, it must be replaced with fresh oil. Oil is usually changed according to a schedule that's established by the equipment manufacturer. Also, in many cases, contaminated oil can be purified and reused. Oils are often divided into several common groups based on the uses for which the oils are suitable. One group of oils is circulating oil. Circulating oil flows or circulates through a piping system or moves freely within a closed area. The circulating oil group also includes hydraulic oil. Hydraulic oil is primarily used to transfer force from one component to another in a system. Sometimes, though, the same circulating oil is used for both lubrication and hydraulics. For example, large steam turbines are often built to use the same oil for lubrication and for hydraulic control. In equipment that's operated in low temperatures, a circulating oil's pour point must be low enough to allow the oil to flow freely. Also, the viscosity index of a circulating oil is very important if the system in which the oil is used experiences large changes in temperature. Gear oil is a type of oil that's used primarily for lubricating gears, although it may be used to lubricate many other devices as well. Various gear oils are available. A gear oil may be a straight mineral oil, or it may contain additives to improve the oil's load-carrying ability and its performance in high-pressure applications. Viscosity is a critical property for gear oil because an oil that's too thin will be squeezed out from between the gear teeth and won't protect them. But the oil must also be able to flow freely enough to help cool the gears. An oil that's too thick will cause the gears to overheat because of high fluid friction. Engine or motor oils contain additives that enable the oils to be used in different types of operating conditions and in different types of engines, such as diesel engines and gasoline engines. This tank truck, for example, uses an engine oil that's specifically designed for heavy-duty diesel engines and relatively severe working conditions. There are many different methods for lubricating equipment with oil. The method that's used generally depends on the equipment that's being lubricated. Manual oiling often involves wiping or brushing oil onto moving parts, such as chains and wire rope. To prevent personal injury when applying lubricants manually, workers must always use the appropriate personal protective gear. Workers must also make sure that the equipment is shut down and properly tagged and locked out before they apply the lubricant. Some bearings have a small oil cup or reservoir that dispenses oil automatically as the oil level in the bearing decreases. To maintain the proper oil level in the bearing, workers must check the level in the oil cup regularly and add oil as necessary. The oil cup should be cleaned before it's used. Dust and dirt that enter the bearing with the oil can lead to bearing failure. Centralized oiling is a lubrication method in which oil is automatically applied to the moving parts of several machines by an independent, centralized oiling system, such as the one illustrated here. But to be sure that the proper oil level is maintained, workers must check the level in the reservoir on a regular basis and add oil when necessary. Finally, applying oil to lubricate bearings is a critical maintenance task in most industrial facilities. One of the most common problems associated with lubricating bearings is over-lubrication. The application of too much lubricant can cause an increase in operating temperature and a decrease in viscosity. Then, if the lubricant becomes too thin, it can't carry the load inside the bearing. As a result, the bearing will fail and have to be replaced. Also, too much lubricant being forced into a bearing may burst the bearing seals. This in turn allows the lubricant to escape from the bearing while contaminants are allowed to enter. Certain properties unique to grease determine the appropriate grease for a particular application. One such property is drop point. Drop point refers specifically to the melting point of a grease. The term is derived from the method that's used to measure this property. The grease is heated slowly until fluid begins to drop from the grease. The temperature at which the drops form is the drop point. If the operating temperature in an area is higher than a grease's drop point, the grease tends to flow away from the area that needs lubrication. So a grease's drop point is normally considered the highest temperature at which the grease can be used. Some greases don't have a drop point. Instead, when heat is applied, the grease begins to decompose chemically before it reaches the point where the thickener in the grease would break down and drops would form. A grease's consistency or stiffness is an important physical property for much the same reason as drop point is. If a grease is too hard, it will be difficult to apply. But if it's too soft, it may flow away from where it's needed. Either of these situations could result in inadequate lubrication and damaged equipment. The consistency of a grease varies with temperature, and there's generally an increase in the softening of a grease as the temperature increases. For these reasons, consistency is a critical property to consider when grease is selected for a particular application. The American National Lubricating Grease Institute, NLGI, has developed a widely used classification system of grease consistencies. In this system, grease consistencies are designated by NLGI numbers that range from 000 for the softest to 6 for the stiffest. If a grease must be pumped through a centralized greasing system, the grease's pumpability should be considered. Pumpability is a measure of how easily a grease can be moved or pumped through a centralized greasing system without clogging the pipes or the components in the system. The water resistance of a grease is an important property if the grease will be used with machinery that can be damaged by water. Many greases break down or dissolve when they come in contact with water, but most greases that contain thickeners such as calcium or lithium soap, which are insoluble in water, resist water very well. The ability of a grease to retain its chemical and physical properties when subjected to extreme temperatures or exposed to reactive substances is referred to as the grease's stability. In many applications, it's crucial to use a stable grease to protect the equipment that's being lubricated. Bearing applications are especially sensitive to instability. If the grease in a bearing breaks down from the heat that's generated during operation, the grease will leak out and leave the bearing dry, causing the bearing to seize. A stable grease, on the other hand, resists breaking down due to temperature increases or exposure to air, water, or reactive chemicals. There are various reasons for using grease, most of which depend on the operating conditions in a given situation. Under certain conditions, grease may be necessary to ensure that the lubricant will stay in place. As long as grease remains semi-solid, it tends to stay where it's put. Oil is much more likely to flow away from where it's needed than grease is. Even when both oil and grease would flow out of an area, it's much easier to retain grease with a seal than it is to retain oil. Keeping the lubricant in place is important because leaking lubricant could contaminate surrounding areas or cause a fire hazard. Another reason for using grease is that grease may be required to assure that contaminants are prevented from getting between lubricating surfaces. In some high-temperature applications, such as this conveying dryer, grease with a high-temperature thickener is used to keep the lubricant in place. It's possible to use oil in high-temperature situations, but additional equipment such as this cooler must usually be provided to cool the oil. Greases are also used to lubricate bearings in low-speed applications that don't generate much heat. Grease is frequently used when the running speed of a plain journal bearing doesn't exceed 200 to 300 revolutions per minute, or RPM. Finally, lubrication doesn't have to be done as often with grease as it does with oil. So grease is commonly used in situations where frequent oil lubrication is difficult to accomplish. In this part, we'll look at some typical examples of how to apply grease for proper lubrication of industrial equipment. Sometimes workers apply grease manually with a brush, clean cloth, or their gloved hands. The workers must use the required personal protective gear and make sure that the equipment is turned off, locked out, and tagged before they apply the grease. Sometimes workers apply grease to operating equipment by turning a screw-type cup to force grease into a component, such as a bearing. The level of grease in the cup must be checked regularly. If the level is low, the cup must be refilled. Anti-friction bearings often have housings that retain grease and help keep out dirt. But a problem can occur if too much grease is put into the bearing, because there's no place for the excess grease to go. Consequently, a way for old grease to leave the bearing must be provided. In this example, the housing has a drain hole. To prepare to grease the bearing, remove the plug from the drain hole and wipe the grease fitting clean. Then connect the grease gun to the fitting and slowly add the specified amount of new grease while the machine is running. Don't overgrease the bearing. Typically, with a hand-operated grease gun, you should apply no more than 3 shots of grease at a time. Next, disconnect the grease gun from the fitting and wipe the fitting clean. Then, allow the machine to run for a few minutes with the drain plug still removed. As the machine operates, excess grease will be forced out of the drain hole. After a few minutes, wipe the drain plug clean and put it back in the drain hole. Greasing a sliding surface bearing, such as this plain journal bearing, is a relatively simple procedure because the design of the bearing housing doesn't cause grease to be retained in the housing. The usual practice is to apply grease to a grease fitting on the housing with a grease gun while the equipment's shaft is turning. This procedure is generally continued until new grease is forced out of both ends of the bearing. Any excess grease will rapidly work its way out. In this topic, we talked about oils and greases and some of the different methods for lubricating equipment with these types of lubricants. To check your understanding of the material that we covered, try answering some practice questions.
Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who have recognized and selected CSI Training as the world leader for quality instructional products. The next 40 minutes will reveal the keys to implementing a successful lube analysis or tribology program. Whether your plant practices preventive, predictive, or proactive maintenance, you will be able to apply the tips and techniques presented here to strengthen your reliability-based maintenance program and save thousands of maintenance and downtime dollars. The study of the lubrication of interactive surfaces in relative motion, such as bearings or gears, is called tribology. So oil analysis programs usually are called tribology programs. The tribology information presented here is not targeted toward the chemist, but to the maintenance technician or plant engineer who must ensure proper lubrication in the machinery for optimum performance and ensure proper management of the lubricants. Some maintenance programs regularly collect oil samples and send them off for analysis, but when the results arrive, the only part read is the one line of recommendations. Then it is simply filed away because a plan is not in place to use the results. Or due to a lack of training, the report is not meaningful. But the lab report is only as good as the information supplied to the lab. We will consider how to develop a plan to use lubricant analysis as a means to detect lubrication problems and mechanical problems, as well as diagnose the source or cause of premature machinery wear. We'll look at oil and machinery conditions that can be diagnosed with on-site lab and with off-site labs. Steps and techniques are shown to collect oil samples and perform tests for certain conditions, and recommendations are made for off-site tests. Then, methods and rules of thumb are shown for setting alarm levels for the various machine parameters and machine types. First, let's look at oil analysis and see where it fits into your maintenance program. There are 4 basic philosophies of maintenance, and we can compare them using a typical example. If a machine is misaligned, excessive force is applied to the bearings, which will cause them to fail prematurely. One maintenance philosophy approaches this situation with a "if it isn't broke, don't fix it" attitude. This is reactionary or run-to-fail maintenance, which is often referred to as hysterical maintenance. When the machine fails, it is usually catastrophic and will then be fixed. Analysis of oil or lube samples from the failure is really post-mortem analysis and will have excessive wear particles, contaminants, and may be degraded due to excessive heat. The second maintenance philosophy avoids these catastrophic failures by looking at the machine from a historical perspective. If it tends to fail every 18 to 20 months, then replace the bearings every 12 to 14 months to prevent a catastrophic failure. This philosophy is called preventive maintenance. Oil analysis programs and preventive maintenance plants tend to only replace the oil at calendar intervals, with the lab reports of the oil condition really having no effect on the maintenance program. And valuable information on machine condition, lube performance, and contamination is lost with each oil change. With the advent of electronics and computer-aided technology, instrumentation has been developed to detect and trend characteristics of failures, such as bearing failure, to get the most life from the machine by replacing it only when it is in progressive stages of failure. Accurately predicting the time of failure can save thousands of dollars from premature replacement of the components. This predictive maintenance philosophy is actually much more involved than condition monitoring and uses many technologies such as vibration analysis, infrared thermography, motor current analysis, and oil analysis to determine the present condition and predict the future for the machine. Predictive maintenance programs have proven savings of millions of dollars in maintenance costs. Oil analysis in a predictive maintenance philosophy capitalizes on the program with early diagnosis of problems, which in some applications go undetected with vibration analysis. Thorough training coupled with precise steps of action for specific lube conditions can be the lifeblood of a predictive maintenance program. Substantial savings are realized from adding oil rather than replacing oil that still has useful life and consolidating oil types for various machines. Additional savings result from reduced waste oil disposal costs. The fourth maintenance philosophy questions why the bearings are not running to a full life expectancy, which can be from 5 to 20 years. It then identifies and eliminates the source or root cause of the accelerated failure. In our example of the misaligned pump leading to early bearing failure, the problem would be corrected by performing precision alignment and not just replacing the bearings before they fail. This is a proactive philosophy requiring a mature management environment which has detailed control, performing cost benefits, certifying new equipment and lubes, providing technical training, and linking all technologies. A proactive philosophy results in dependable maintenance operations called reliability-based maintenance. To achieve this RBM approach, the vibration analyst also has a working knowledge of tribology, with on-site capabilities as well as an electronic link to an off-site lab for results and a direct link to a computer maintenance management system for immediate responsiveness. Oil analysis in a reliability-based maintenance environment has the greatest potential for savings because the root cause of oil contamination, degradation, and machine wear is searched for and corrected to achieve maximum life for the machine and the lube. To achieve these optimum results and avoid a meaningless loop, your plan must have a purpose with specific pre-planned actions for particular events that will lead to the goals of improved lubrication quality, reduced machinery wear, extended oil change intervals, reduced oil disposal costs, and reduced oil sampling costs. The plan begins with identifying machines and processes which are critical to plant production or critical from a safety standpoint. Next, document the lube type and the environment it is used in. Then establish alarm limits and target cleanliness levels along with the required oil testing appropriate for the machine type and lube type. Train all personnel involved so each one will have the big picture of the lube analysis program, as well as the specifics for proper sampling, handling, and testing of the lubes. Now you are ready to jump into the loop shown earlier, but provide more steps and exits from the loop. The first step in the loop is collecting proper samples. Then screen the sample for extreme conditions using on-site capabilities and well-trained personnel. If necessary, send the sample to an off-site lab for additional diagnosis. If additional diagnosis is not necessary, bypass this step and store the results in a computerized database. Obtain the off-site report and store it in the database. The next step is most often ignored or overlooked, possibly due to inadequate training. Compare the results and trends with complementary predictive technologies. Comparing trends of vibration data of bearing frequencies, for instance, along with trends of iron in the oil viscosity, and large particles can confirm the bearing condition. If temperature data is available, its trend could also provide useful information. Based on these findings, schedule any necessary maintenance and generate management reports. Although this is often the end of the loop, to build the program on a reliability-based maintenance philosophy requires you to exit the loop and use all the gathered information to remove the root cause of the problem, improve the quality of the lubrication, reduce the wear on the machine, and avoid catastrophic failures. When collecting oil samples or handling new or used oils, remember to follow the standard practice procedures for health and safety established by your company. A key factor in oil condition monitoring is consistency in collecting samples. Any oil monitoring program will fail if careful attention is not paid to sampling technique. For that reason, sample from the same location in the same manner and under the same machine conditions. In general, oil should be sampled from a location where the oil is well agitated or flowing. Take samples just after the equipment has been shut down or when it's safe while the equipment is operating. It is important to sample before particles and water have time to settle out of the oil. Samples should normally be taken upstream of any filter. If the oil is sampled on the downstream or outlet side of a filter, the debris and particulate contaminants will have been removed by the filter. Please remember to always consider safety when sampling hot oil from running machines. Because on-site tests are relatively inexpensive and under your direct control and interpretation, be creative and don't be afraid to tailor unconventional sampling techniques to your specific needs. Just remember to apply common sense in correlating your sampling technique and test results to your application. When drawing oil through a drain plug or valve, don't collect oil during the initial spurt or rush. It may contain metal from the plug threads, and it will certainly contain debris that is collected over time around the plug or valve opening. Don't take the cap off the clean sample bottle until you are ready to take the sample. As soon as the sample is taken, replace the cap. This will help to keep the dust, moisture, and dirt out of your sample. Fill the bottle about half full. This makes it easy to completely mix the sample by shaking prior to testing. When using a suction pump to draw oil up from a sump through a fill pipe, dipstick tube, or other orifice, don't let the plastic tubing scrape dirt from outside the orifice or from the bottom of the sump. On the other hand, if you are concerned about free water in the system, go ahead and sample from the bottom of the sump. But remember, always change or clean the sampling tube between samples. As a general practice, you would not want to initiate a maintenance action on the basis of an oil sample taken directly from a used oil filter. However, this is where you will find the highest concentration of solid contaminants and large wear particles. If the filter is free of metallic debris, it is unlikely that much wear has taken place since the filter was last changed. Label each sample bottle with the oil type, the machine from which the sample was taken, and the sampling date. If a sample is diluted prior to testing, the label should reflect that fact. A sample taken from an unknown source has no value. Mislabeling of your sample might lead to unnecessary and costly maintenance actions. These samples hold a lot of information about the oil and the machine, but special testing is required to get that information from these samples. Oil analysis can be compared to the analysis of blood samples in the medical profession. If all that's needed is blood type, then one simple in-office test is performed. However, there are over 900 specialized tests for blood to determine the presence of particular antibodies and diseases, germs, chemicals, and bacteria. But usually only a few tests are run on any person. with the most advanced tests being performed in an off-site lab. Machinery lubricants can be analyzed similarly, and for each machine, there may be only a few tests required. And like blood tests, an instrument produces specific results, so many instruments may be required for multiple tests. These devices here are tools commonly used for on-site oil analysis. Each of these is designed to provide particular information about the oil. There are two categories of information testing provides. One is about the condition of the oil itself, and one is about the condition of the machine. For the oil, you want to know the lube quality, including the condition of any additive package, if there are any contaminants, and whether it is the correct oil for the particular application. The machine condition is determined by examining the wear particles for size, shape, and the materials such as ferrous and non-ferrous metals. Various systems and applications require different lube conditions, such as hydraulic systems and machine tooling, which require exceptional cleanliness, and gearboxes, which by their very nature tend to produce more wear. These applications require particular oils and additives, especially suited to the demands of the system, and should have different standards of cleanliness. The most important parameter of a lubricant is the viscosity. Viscosity is the measure of a fluid's natural resistance to flow. Oils flow more freely at higher temperatures and are resistant to flowing at lower temperatures. So the measurement must take into consideration the fluid temperature when measured. Viscosity is measured in centistokes at the temperature in degrees centigrade. There are tables for the viscosity of each oil at 40 degrees centigrade or 104 degrees Fahrenheit and 100 degrees centigrade, which is 212 degrees Fahrenheit, or the boiling point of water. When the viscosity at 40 degrees centigrade and 100 degrees centigrade is plotted on a special scale, then the viscosity at any temperature can be calculated and then compared to the sample to determine whether it is the correct lube for the machine. Each machine has characteristics that demand a particular lube viscosity for optimum performance. High-speed machinery must use a low viscosity or lightweight oil, while the lube of slow-speed machinery should be higher viscosity or heavier. Since the lube should provide a film between internal components, heavier loads such as gearboxes require a heavier oil. Light loads require a light oil, and if a heavy oil is used, extra energy is required to move the components, producing heat and degrading the oil. High-temperature applications require higher viscosity or heavier oils than colder operating temperatures. Viscosity must be adequate to separate the moving parts at the operating temperature of the machine. When a machine must operate in both cold and warm temperatures, such as outdoor applications, an additive package called a viscosity improver can be added to the oil to make it perform suitably in both environments. If an oil has a viscosity of 17 at 100 degrees centigrade, it may have a viscosity of 140 at 40 degrees centigrade, and a viscosity of 1800 at the 0 degrees centigrade or the freezing point of water. The 17 may be acceptable, but when the machine must be started in cold weather, the oil is too heavy. The viscosity improver does not affect the value at 100 degrees centigrade, but reduces the viscosity at the lower temperatures. Oils such as this are referred to as multigrade oils and are commonly used in automobile and truck engines. The viscosity of an oil in a machine is a key to quickly determine whether the correct oil is in the machine, and on-site oil analysis should have the capability of measuring viscosity. Methods of measuring viscosity include timing the flow through a calibrated capillary tube heated to 40 degrees centigrade or 100 degrees centigrade, timing an object to fall through oil, and measuring the drag on a disc spinning in the oil. This digital viscometer uses a patented free rotor system to measure viscosity and the oil temperature, recording the information in a database to be used in conjunction with other analyzers and devices to trend your oil condition. Compare this measured viscosity against the machine manufacturer's recommendations and against new oils to verify they are correct. Oil viscosity in a machine can change due to chemical, mechanical, or process influences in the system. Viscosity increases due to oxidation, foaming or cavitation in a pump, emulsion with water, solids contamination, and the wrong makeup lube added. Decreases in viscosity are caused by fuel or solvent contamination, refrigerant leaking into the system in air conditioning systems, non-emulsified water contamination, molecular sharing or chemical breakdown, and the wrong makeup lube added. A change in viscosity of 10% is a good indication of a lubrication problem, and checking viscosity is the simplest and quickest method to check for a wrong lube. Maintaining lube quality is a key to ensure consistent, smooth-running machinery. Degradation removes the lubrication properties and may destroy some of the additives. The primary sources of oil degradation are oxidation, sulfation, nitration, and soot loading in diesel engine applications. These all increase acidity and deplete additives. Oxidation is any chemical change due to interaction with oxygen, usually in the presence of heat. Iron oxide, for example, is rust. The effects of oxidation are seen as the sticky residue lining in the sides of oil storage tanks. This gummy residue is called varnish. Sulfation is a chemical reaction with sulfur and is usually found only in diesel engine applications. Soot as a byproduct from combustion process is also usually present. Nitration is the chemical reaction with nitrogen. Oxidation, sulfation, and nitration all increase the viscosity, darken the oil to a reddish-brown color, and increase the acidity of the oil. The increased acid in the oil causes corrosion to your machine, so that instead of protecting the machine, the oil actually accelerates degradation. To check the oil quality for degradation and any other gross chemical changes, the Oil View Analyzer compares a used oil sample with a clean oil sample of the same type used in that application. The changes in the oil chemistry are detected capacitively by the Oil View sensing grid. A full test must be run on the new clean oil as well as the used oil because, unfortunately, the new oil samples sometimes have dirt and water and must be inspected periodically to ensure harmful contaminants are not being introduced into the system. When the new lube is tested, it is recorded in a database for easy retrieval and comparison with future samples. After proper setup, used oil samples are well shaken and tested for 500 seconds or about 8 minutes, comparing the results to a reference oil. The comparison of the two can be displayed graphically and are noted in the indices with recommendations reported in the automated diagnostic function. This analyzer provides a good indicator of any chemical changes that result from soluble fluid contamination, increased acidity, the occurrence of oxidation, sulfation, and nitration, as well as the presence of soot. The on-site tests for lube quality provide instant results assuring you of the vital functions of the lubricant. We have seen that we can perform on-site tests to verify that a lube is the correct one and to determine any chemical degradation that could lead to a loss of performance. There is another area of concern about the lube that should be analyzed, and that is the presence of any contaminants. Contaminants include any foreign particles from outside the oil system getting into the oil. These include water, fuel, coolant, dirt, dust, process fluids, and other solid or fluid contaminants. These particles range in size from 1 micron up to several hundred microns. A micron is 1/1000th of a millimeter, which is about 1/25th of a mil. Human hair is 75 microns, and the unaided eye can see objects as small as 40 microns. Precision valves and pumps have clearances of 25 microns or less, and the thickness of the oil film in a bearing under heavy load can be less than 1 micron. Since bearing clearances can be so small, even minuscule particles in the lube can cause severe damage to the bearing surfaces. Detection of these in the oil can be performed on-site with 2 instruments. One is the 5100 analyzer and the other is the 51PC particle counter. The analyzer tests for water, coolants, and other fluids, while the particle counter uses a laser beam to detect and measure the size and number of solid particles per milliliter of oil. They are categorized in size ranges of 2, 5, 15, 25, 50, and 100 microns. Studies show that the cleaner the oil, the longer the machinery will last. Therefore, it is important to continually increase the cleanliness levels of critical equipment. A typical sample may have many particles in the 2 to 10 micron range and not be abnormal. There are 3 rules of thumb concerning particle contamination. First, for most mechanical systems, clean operations, if particles are less than 25 microns, the equipment is generally operating satisfactorily. Secondly, the larger the particle, the greater the damage, and an increase in the number of particles indicates an increase in the amount of damage. When a sample is abnormal, then send it to an off-site lab to analyze the particle type and determine whether it is a contaminant or actually a wear metal. The most common contaminant is silica, which is sand or dirt, and its crystalline structure is much harder than machinery components, even carbon steel. It is 3 times harder than the case-hardened surface of the races of a rolling element bearing. Since 2/3 of the Earth's crust is covered with silica, it is a very likely contaminant which can enter the system through the breather of the oil sump. When silica is present, wear particles are usually present also. Maintenance personnel must find the source of any contaminants and remove it before it degrades the oil and promotes machine wear. Simply changing the oil may remove the contamination in the system, but if the root cause of the contamination is not removed, it will quickly become contaminated again. Changing the oil when it is not degraded is wasteful. After identifying and removing the source of the contamination, then take the steps to clean your contaminated oil. Wear particles indicate the machine's condition and are measured similar to contaminant particles but are different materials and are usually larger in size. The only time that ferrous material or iron will be in the system is as a result of wear. Ferrous wear can be checked in-house using the 51 FW ferrous wear monitor and works equally well with oil or grease. It is a quick tool requiring only 10 seconds per sample for the vibration analyst to use to detect iron particles and then confirm the problem with a vibration analysis. The 5100 Oil View Analyzer uses electromagnetic separation to detect the presence of ferrous particles on a sensor grid. A microscope can be used to determine the cause and source of these abnormal wear particles. One group of wear particles is caused by a 3-body system. A system typically has a 2-body system, that is, 2 components of a bearing, for instance, are separated by a thin oil film. When a 3rd body, such as dirt or silica, is in the film, it will cause scraping or gouging of the bearing components, creating a long, narrow particle similar to a machining swarf. When this abrasive wear is present, find the source of the abrasion and remove it. Check the breather for possible influx of contaminants and make sure the filter is adequate for the application. Fatigue wear occurs when components have been flexed due to repeated changes in loading and they simply come apart. The root cause may be misalignment or unbalance, but the extra load placed on bearings, shafts, and other components causes separation in the metals. This is the spalling that occurs in bearings or gears, and when examined under a microscope, will be chunky in shape. This fatigue wear should alert you that the components are nearing the end of their life. An anti-wear additive, sometimes called an extreme pressure additive, can be input into the system at this point and may extend the life to a scheduled outage. Laminar particles are similar to plates and may be round or oblong but thin and have parallel lines in one direction. These are from severe sliding or adhesion wear and can be the result of a rub, imbalance, or misalignment. These 3 wear particle types, the abrasive, fatigue, and the adhesion, can be ferrous or non-ferrous metals, although typically 80% of the wear particles are steel or cast iron ferrous particles. Non-ferrous wear metals are copper and copper alloys, chromium, molybdenum, aluminum, lead, tin, silver, nickel, palladium, and titanium. The copper alloys will range in color from salmon pink to brown, with varying shades of yellow. Nickel and chromium will be bright silver in color, while tin, lead, and aluminum will be various shades of gray and white. The particular metals may be difficult to distinguish in on-site capabilities, but you can screen the sample to verify the correct lube. Check for degradation and acidity. Determine the presence of contaminants, including water, processed fluids, and solid particles. And determine the amount and size of wear particles, especially ferrous wear particles. When any of these oil or machine condition indicators are in the abnormal range, Send the sample to an off-site lab for further analysis to determine the exact contaminant, wear particle sources, and the condition of the additive package. An off-site oil analysis lab designed especially for handling industrial oil samples, such as CSI's tribology lab, has the equipment and expertise necessary to provide detailed analysis of your lubricants to help you maximize the life of your machines. In your on-site lab, you can detect particles in the oil, but here we can provide the exact molecular makeup and elemental analysis which can help you determine the source of the contaminants or wear. When a sample arrives at a lab, it is logged into a database, recording any information you provide about the oil, the application, the process, and the equipment, including bearing types, gear types, and its working environment. The sample is then processed through the FTIR, or Fourier Transform Infrared Workstation, to measure the chemistry or molecular structure of the lubricant and contaminants within the lubricant. It uses an infrared light source transmitted through the lubricant film, measuring the absorption of the discrete infrared wavelengths by the fluid. The absorption is due to oxidation, sulfation, nitration, glycol, or water, which each have a particular wavelength. The spectrum is searched for these particular wavelengths and compared with a reference spectrum to determine their presence in the lubricant. This FTIR analysis is performed first with its results pointing to other tests and measurements that should be performed, such as the total acid number or the Karl-Fischer test for water. The sample is then processed through these two capillary viscometers to determine the exact viscosity and analyze the quality of the base stock. The oil is deposited into capillary tubes where the flow is timed after it is heated by the solution to 40 or 100 degrees centigrade temperature. The viscosity is measured in centistokes and then given the corresponding viscosity index. An oil that is extremely different at 40 and 100 degrees centigrade will have a lower viscosity index indicating a lower quality base stock, while an oil whose measurements are fairly close will have a high index number indicating a good base stock. This measure provides extremely accurate information, allowing you to compare it to manufacturers' recommendations and reference samples. The next analysis is the spectrometric oil analyzer, which determines the elements in the oil. Each element emits precise spectral colors when ignited, and by igniting the sample and measuring and separating the wavelengths of color light into the color spectrum, the elements that are present are determined. The well-mixed oil solution is placed in a 1 milliliter bath with a carbon wheel dipping into the bath, bringing it up to another carbon electrode where the oil is energized, igniting the particles. The spectral colors are summed to determine the total amount for each element. The elements are recorded in parts per million for particle sizes less than 10 microns. The tests detect and measure contaminant metals, additive metals, and wear metals. Contaminants such as sodium, potassium, and boron are indicative of coolant leaks, while silicon is from dirt getting into the system. Additive metals in the fluid can indicate the level of degradation by measuring the depletion of the elements that make up the additive package and trending it over the sample periods. Common additive metals are magnesium, calcium, barium, phosphorus, zinc, and sometimes molybdenum. Wear metals detected are iron, chromium, copper, aluminum, molybdenum, lead, tin, nickel, and silver. Because the spectrometric oil analysis does not address particles over 10 microns in size, when any of these wear metals are detected in abnormal amounts, the sample is tested on the ferrous wear analyzer, and then a full wear debris analysis is performed. The wear debris analysis workstation separates iron from other particles in the fluid by using a vibrating magnet separator, and the non-ferrous particles can be poured off and analyzed apart from the ferrous particles using a microscope. The particles are classified by the type of wear material, the actual sizes, shapes, textures, and the average density per square millimeter. The wet chemistry automated workstation measures the total acid number and gives a precise measure of water in the oil using the Karl-Fischer test. It is used when the FTIR analysis indicates oil degradation or that water is present. The TAN of a new lubricant should be 0.0 to 2.0. An increase in acidity by 2 points or 50% indicates there is a real problem with acidity. Water content in a lubricant should be low when the lubricant is new and goes higher over time due to condensation or leaks in the system. Trending these characteristics from the new lubricant condition provide a picture of water contaminants and oil quality by the presence of acid, indicating the oil may be affected by oxidation, sulfation, and nitration. The lab results can be accessed by your computer via modem for instant access, complementing your on-site analysis, enabling you to make the vital decisions about the life of your machine. A chemical company refused to implement an oil analysis program, claiming that oil analysis did not work. They showed a sample taken from a pump that was sent to an oil lab for analysis. The lab tested the sample and gave it a clean bill of health. Less than a week later, the pump failed. Why did the oil lab give the sample a clean bill of health? Did the sample really have information that would indicate a problem with the machine? The test performed by the lab was a spectrometric oil analysis, which is a good test to determine the elements present in the oil. The results were in the normal range. What went wrong? Remember that earlier we used the analogy of tests performed on blood to determine the illness. A blood sample would not have the same test run for a common cold as tests for cancer. It would not be wise to perform just one test for any condition, but instead tailor the test for each condition. The spectrometric oil analysis is only able to flash or burn particles that are 10 microns and smaller. When the sample was tested again for large wear particles, it had excessive ferrous fatigue wear chunks in excess of 250 microns. They were so large, they were ignored by the spectrometric oil analyzer. A failure progression typically begins with wear particles in the 10 to 20 micron range, increasing in size and number until failure. Wear particles in the final stages can be in excess of hundreds of microns. Wear particles give the best indication of the severity, but may be overlooked with spectrometric oil analysis. This problem could have been avoided if a plan had been in place to test the oil based on the machine's needs or profile. A profile is a series of oil tests designed for machines with specific characteristics. A turbine, for example, does not have the same lube requirements as a gearbox and should not have the same tests. There are many profiles, but they can be grouped into 4 basic profiles. One is a clean systems profile, which includes turbines, hydraulic systems, machines with sleeve bearings, and extremely critical contamination-sensitive systems. On-site analysis for clean systems should include viscosity, degradation, and particle counting. The laboratory analysis should include spectrometric analysis to test for additives, viscosity index, FTIR to test for molecular degradation and water contamination. Industrial drives such as gearboxes, crushers, chippers, and stamping processes should be tested for ferrous wear and wear debris analysis, as well as checks for viscosity, water, and other contaminants. Off-site analysis should include a full wear debris analysis, viscosity, water contamination, spectrometric oil analysis for the additive condition, and the FTIR to determine degradation. The industrial preventive profile includes common pumps, fans, compressors, and engines. Tests should include all measurements the 5100 analyzer performs for contamination, degradation, and wear. The lab test should be the FTIR, the viscometer, spectrometric oil analyzer, and the ferrous wear monitor. The last profile is grease, which should be tested in-house with a ferrous wear monitor. Lab tests should include a wear debris analysis, ferrous wear index, and spectrometric oil analysis. All machines are not the same, and all oil tests should not be the same. And just like vibration alarm levels are unique for each machine, the oil quality levels and cleanliness levels are unique for each profile and machine type within a profile. Standard machinery guidelines are usually provided by the original equipment manufacturer, the oil analysis laboratories, and the lubricant supplier. These sources provide good starting guidelines, but just like vibration alarm levels, they must be tailored to the machine based on oil trending, target cleanliness levels and the maintenance philosophy of your plant. Earlier we showed the oil analysis loop and pointed out the need for a plan before any benefits can be realized from a complete tribology program. The plan must identify the critical machine, the profiles, and the alarms, along with a goal of desired results and a training program to qualify all personnel involved. The main program loop samples at regular intervals, screening them for abnormal conditions, and sends the abnormal samples to an off-site lab for further analysis, while OK samples are stored on-site, with the data stored in a database for comparison and trending with other predictive maintenance technologies. Now you can see the data and plug the information into a computerized maintenance management system, schedule maintenance actions for the machine, and generate management reports documenting the increased reliability, improved quality of the lubricants, and the reduced lube procurement and disposal costs. Completing this loop with the plan and results in place means that your data, including the old data, is working for you, enabling you to have a reliability-based maintenance program. As you implement your oil analysis program, there are a few things you should remember that will help your oil analysis program have immediate successes. First, if a machine failure occurs, thoroughly clean out all wear debris before refilling the system. If it is not cleaned out and flushed, the wear debris will quickly cause another failure. Observe how oilers handle the oil for the various applications. Many times the wrong oil was used because it was closest, and the oiler did not realize the severity of using a different oil. Proper training can help avoid this common problem. If you have a product performance problem, check that the product in storage is protected from dirt and water. Also check the apparatus used to transfer the oil. Look for an outside problem before looking at the oil. Eyeball the sample before you send it to the lab. If the sample looks milky, water is present. If you have foam, ask if a defoamant has been added. Foam does not lubricate well, but gearboxes tend to whip the oil into a frothy foam, causing air entrainment. In other words, visually inspect the sample and use common sense. Do not be too quick to blame the oil or grease in an oil-related problem. Look for outside sources of contamination and adverse operating conditions. Always use clean sample containers. Resample to ensure a representative sample. These troubleshooting tips seemed obvious, but are sometimes automatically ruled out because they're obscured by the pressures of providing a fix to the current problem. While many areas have been covered, we've only highlighted the most common oil analysis practices and characteristics. We realize that unique design and applications necessitate special considerations for oil analysis programs. Thank you for joining the thousands who have recognized CSI training as leading industry with quality information, instruction, and application of PDM and RBM techniques and products. Whether your plant currently uses preventive, predictive, or proactive maintenance practices, we're confident that the application of these tips and techniques will help you succeed in your oil analysis program. We look forward to assisting you achieve success in your future endeavors.